Hello and welcome, pre-calculus classes. This is take two of spring final exam review video, and this is a part 2 as well. You know, we're in chapters 4 through 6. Last time we were chapters 1 through 3. We're going to get an abundance of example problems from the following topics here: evaluating, solving trig functions, graphing trig functions, law of sines and cosines, areas of triangles, and vectors in the coordinate plane. At the very end, there will be some things involving complex numbers as well, but you know what? They have to do with trig. It's all about trig form for those complex numbers. So, you know, buckle up or sit back, relax, you know, just whatever way you want to say it. Brace yourselves, right? Follow along with this. Understand that when I'm doing these problems, for the sake of time, it's less of the teaching, more of just the doing, right? I want to do these as if we've learned them before and only speak on some things while I'm writing to make the process go a lot more smoothly. And you know, someday this will be you and you'll be all ready to walk down the aisle, and I don't know. Let's go and get started here. Numbers 1 through 4, we are going to convert each degree measure into radians. One way of going about it, of course, is dividing by 180 and reducing that fraction. I'll kind of avoid those steps here. What we know is for special right triangles, we know that pi over 3 is 60, pi over 4 is 45, pi over 6 is 30, pi is 180, pi over 2 is 90. If you can come up with 150 as a multiple of one of those numbers, for example, 30, negative 150 is the same as factoring out a negative 5 and being left with 30 inside. If you can do that, you've done a straight conversion here. 30 is pi over 6. So this is negative 5 pi over 6's. So total, that's negative 5 pi over 6. That is the radian equivalence to this degree measure right here. Negative 5 pi over 6 radians. Number 2 is more of the same, only this one's probably significantly easier because you're dealing with a special right triangle that you already know, or a special ratio here. Pi over 4, we know pi over 4 is 45. So negative 45 must be negative pi over 4. And that's just the answer there. See, there's not much to do with it if you're really vested in at least those radians. 135 degrees, also a multiple of 45. Now look, if it was a higher multiple as well, we would, we could figure out what that is, or if there was a lower one, we could figure out what it is. But I know it's got to be a multiple of 45 and not 30 or 60 because it ends in a 5, right? It ends in a 5, and 30 and 60 can't get you multiples that end in a 5 like this can. This could be 3 pi over 4, 3 45s, 45, 90, 135, boom. Other multiples, obscure ones, are 225 and 315. Those ones come up as well within the first 360 degrees of a unit circle. Finally, problem number 4, 150 degrees. Look, the first one was negative 150 degrees, so I don't know how much more we have to say about it other than it's 5 30s again. So it's 5 pi over 6's, only now it's the positive answer. So you get number 1. I think you get number 4 then as well. That's the radian equivalent. Convert each radian measure into degrees now for numbers 5 through 8. Now, number 5, you have some options here. If we think about it like the last set of problems we did, what I can do is take that 17 away from pi over 6, think of what pi over 6 is, which is 30, and do 17 times 30. And don't think I'm going to take out the calculator for this, which, by the way, I have to open up that program in a bit. 17 times 3. Come on, here we go. 17, 34, 51. So 51 with a 0 at the end would be how many degrees this is? 510. If you're not able to do it that way, one other way that you can think about it is, let's split up 17 pi over 6 into, let's get 2 pi, which is 12 pi over 6, added out, or subtracted away from the rest here, which is 5 pi over 6. So 12 pi over 6 is 2 pi. That's 360 degrees. 5 pi over 6, as we just saw from numbers 1 and 4, that's 150 degrees. So if you know your 360 here, take that out, see what's left. And if you know this one enough, I think that's going to help you. That equals 510 degrees as well. Number 6, negative 2 pi over 3. This time, because the number is small enough, I will take this number out right here, multiply it by pi over 3. Pi over 3 is 60. Negative 2 times 60 is negative 120 degrees. Not much else to say on that. If the answer is negative, keep it negative. Excuse me. Number 7, negative 8 pi over 3. Kind of back to this first one, it's a little more than 360. So I'll give you two approaches again. 2 pi, when divided by 3 here, not 2 pi over 3, but 2 pi is 6 pi divided by 3. So I can take that out, minus also 2 pi over 3. That's going to give you negative 8 pi over 3. So here's your negative 360 minus 2 pi over 3, right? This was 120 degrees. That's going to give you negative 480. There's one approach. Second approach is taking negative 8 out from pi over 3. That's taking negative 8 out from 60. That's also going to give you negative 480 degrees. As long as you can multiply stuff like that, then you'll probably be set. If you take a while to multiply them, then consider all of your options that you have. And finally, 4 pi over 3. This one right here, again, taking 4 out of the pi over 3. A lot of these were pi over 3s, huh? So 4 out of 60 there, and not 4 out of, but factoring the 4 out of there, and you're left with 240 degrees if you multiply it back in there. Now, one other thing I can say, at least for this problem, before just rushing on over, is that 4/3 is more than 1. 1 pi is 180, so 4/3 pi is more than 180. So at least I know, it's not that I know the answer is correct, but I know if I got 140 as an answer, I would know there would be a red flag there, right? There would be something wrong, and I'd have to address that for sure. Number 9 and 10. In each problem, angle C is a right angle. Find the angle indicated to the nearest tenth. Yeah, I started saying this motto with conic sections, but I could have said it a long time ago as well. When in doubt, draw it out. They're saying angle C is a right angle. That's fantastic. You know, I don't see a drawing with it though, right? So I think we'd all prefer, let's draw a right triangle. Here's C. Let's give ourselves A, and you know, because we're going to find A, and here's a lowercase b, that's referring to a side length. So assume the angle opposite's a capital B. We're looking at triangle ABC. C is the right angle, which means opposite big C is little c, which is the hypotenuse of 14.3 units. And B is 8 units right here. So a little b. So what we're looking for is the measure of angle A, this angle right here. So what we're going to do in a case like this is use trigonometry, just like we saw degrees and radians, and we'll be doing trig on those as well. Here's a ratio, and this side length here is adjacent to this angle measure here, and this is the hypotenuse. So in SOHCAHTOA, we will use cosine. Cosine of the measure of angle A, which we do not know the answer to, is 8 over 14.3. So A, you want to get it by itself, you're going to have to take the inverse cosine of both sides. Inverse cosine of A is just A, and inverse cosine of 8 over 14.3 will give me some angle measure. Now this is where we go to the calculator in order to be able to round to the nearest tenth, right? That's what they're asking for, not just an exact answer. So first of all, make sure your mode is in degrees here. Make sure you're not in radians because, you know, this measure of angles and such, you know, we use degrees for these kinds of things. Let's go second cosine, and then 8 divided by 14.3. And we get a number, 55.98. Okay, they do say round to the nearest tenth here. So this guy here is about, you know, 0.98 rounds up to 10, you know, to 100, right? And that carries over into here. So about 56.0 degrees. That's rounded to the nearest tenth. 0.0 for precision. Number 10, same kind of idea, different setup, different letters, different numbers here, but still C is the right angle. So we have C. We know the length of side length A now. If I want to call this A up here, then side length of A is 11. Here's angle B, which looks like we don't need to know anything about B. Wouldn't you need to know that this was the letter B? It might not be. Who knows? They don't say anything else about it. So this is 12.2, which is side length C right there. But let's fill that out. Okay, we're trying to find measure of angle A one more time here. This time, we don't know the side adjacent to it, but we do know the side opposite to it and the hypotenuse. That opposite hypotenuse in SOHCAHTOA is sine. This time we will take the sine of angle A, and that's going to be 11 over 12.2. Much like last time when we took the inverse cosine of both sides, this time we'll take the inverse sine of both sides, which leaves A by itself. A is going to be equal to the inverse sine of 11 over 12.2. Okay, and that approximation we will find out here momentarily. Let's go inverse sine, second sine, and 11 over 12.2. Whoops, that looks like a 1, not 11. 12.2 right there, and about 64.37, so 64.4 degrees. Okay, that would be your final answer there. Now look, I almost had a typo there. I almost put 1 over 12.2. I think I would be able to note that my answer is incorrect in a red flag kind of way. Check out this angle, 4.7 degrees. And that's not to say that 4.7 can't be an angle that we get here. But can you really believe that a right triangle with a hypotenuse of 12.2 and a leg length of 11, and that's really close to 12.2. I mean, it's 64.4 degrees worth of length there. But remember, the smaller the angle measure is, like if I redraw a triangle here in red, the smaller the angle measure is, the smaller the opposite side is. Okay, so if this was really 4 degrees like that here, this couldn't possibly be 12.2 and this be 11. I mean, I don't know if this is drawn to scale or not, but that's much more to scale than this would have been in this other case. So if I did type that out, something would have been very wrong. I would have had to note that, right? That's one of those red flag moments that really helps you out when you accidentally make a mistake like that. But anyway, that's number 10. We get that answer there, rounded to the nearest tenth. Number 11, find side length of B. Same situation. We still have angle C is a right angle, etc. Now we got to find the side length of B. So finding a side length instead of an angle measure. Not necessarily harder or easier, just different. Got to do different steps. ABC, let's stick with that. Not drawn to scale except for the C. Measure of angle B is 28 degrees. Definitely not drawn to scale there. C, side length is 4. We need to find side length B, which what you do need to know is opposite your angle. So side length B right there. We know nothing about A, even if A is the letter. So this angle here, I'm trying to find the side opposite. I know the hypotenuse. This is once again so in SOHCAHTOA. So we will be taking the sine of angle B, which is 28 degrees. And its ratio is B over 4. If I'd like to get B by itself, as it's dividing by 4, I can multiply both sides by 4. So B is going to equal 4 times the sine of 28 degrees. And I'm still in degrees in my calculator. I'm going to round this number to the nearest tenth here. 4 times sine of 28 looks to be 1.877, so around 1.9 units approximately. I won't write the units here, but they don't give you units either, so it's just about 1.9 in length. Pretty nice. Number 12, we're going to find side length A, now given angle B, and side length C. So given kind of the same drawing here, I wish I could just paste these over somehow. But given the drawing here with ABC, okay, B is down here at 53, C is 11, A is opposite angle A. So if I know angle B here, I'm going to find angle A, which is adjacent to it, and I know the hypotenuse, I'm now going to be using cosine. Adjacent over hypotenuse. So the cosine of 53 degrees is A over 11. So A equals 11 times the cosine of 53 degrees, which is about, we will find out, 11 times cosine of 53. Oh, about 6.6 units there, rounded to the nearest tenth. Sounds good. I like it. Find the value of the trig function indicated. We want to find cosine of theta when this is theta. Okay, well, let me just quickly tell you what they're not asking for. They are not asking for what this angle measure is, just like the last time. They're asking you to take the cosine of it. So that means write out its ratio. And look, I'm going to take the calculator away for now because they are not asking us to round this ratio either. In the end, and you can probably see it on your answer key, which I assume, I don't have it in front of me, but I assume is the case, your answer is a fraction. So what they're asking you to do is take cosine of this, given what you have here. Adjacent is 18. Hypotenuse is 9 root 5. So 18 over 9 root 5 would be your answer if this fraction was reduced and simplified. By reduced, I mean 18 can divide by 9, and you'll be left with 2 over 1. So this is 2, all divided by root 5 here. And by simplifying, I mean that this is an irrational denominator. So let's multiply top and bottom by root 5, and you'll be left with 2 root 5 all over 5. That would be the proper ratio for the cosine of this theta right here, at least in reduced simplified form. Number 14, sine of theta. Okay, theta is right here. Opposite is 21. Hypotenuse, look, hypotenuse we don't know. Okay, so we actually got to find it in order to do sine of this thing. And what other way than in a right triangle to use Pythagorean theorem with the other two side lengths we do know. So we know that a squared plus b squared equals c squared here. The only question is, will this number come out cleanly? Okay, so 21 squared, 21 times 20 is 420. So plus another 21 would be 441. Again, this is one of those, I don't know, you can do it without a calculator. It's totally possible to do. The only question is it a matter of convenience or not there? 2 squared was 4. Root 22 squared is just 22. That equals c squared. So this is 441 plus 88. And c squared is c squared is 529. We will take the square root of both sides to find out what c's length is here. Now, if you don't know your perfect squares here, to be honest, I don't know what this perfect square is right here, if it is one. But what you do, again, is break this thing down. Maybe use your calculator, but break it down until you figure out that it's got to be more than 20 and less than 25. I'm going to guess it's 23. So 23 times 23 here. Think about 23 times 20. Here, let's do it mentally. 23 times 20, that's 23 times 2, 46 with a 0. And then 23 times 3 is 69. 460 plus 69, oh yeah, is 529. So c equals 23. It was an exact length. And if it wasn't, look, you'd have to simplify the radical or what have you here. But as this problem's set up, it's nice. So sine of theta, in this case, opposite over hypotenuse is 21 over 23. Again, I'll use the calculator as little as I need to here. I'm only going to really use it with the trig stuff that I have. Oh, that was 14. Okay, that's fine. Let's move on. Number 15, find the measure of the indicated angle to the nearest degree. I assume it's the question mark here, so let's call it theta instead. Let's use a variable we like. So find the measure of the angle. It's kind of the same as the last set that we had with triangles ABC, where C was the right angle here. I'm going to take the cosine of theta here, because I know the adjacent, I know the hypotenuse. We haven't run into tangent yet. And to get theta by itself, I'm going to take the inverse cosine of both sides. So remember what I said last time about a certain answer to expect, especially if you type something wrong in the calculator by accident. So going back to our calculator here, let's round theta. What I was going to say about this here is, not because of the drawing, but I expect my answer to be a lower angle measure, a smaller number, because 31 and 32 are very close alike. And for a right triangle, that's not going to be possible unless you're looking at a rather low angle, maybe in the teens or so. So we'll do inverse cosine of 31 over 32. We land on 14.36 degrees. I trust it. Hey, at least it's less than 45, right? If I got something more than that, it's about 14 degrees, nearest degree. If I got 45 or more, now there's a red flag concern. Number 16, we got our theta here now. And hey, look, adjacent and hypotenuse. It's once again cosine. So without having to vary it up too much, the process remains the same. Being able to answer the question as asked is obviously key here. So going through the motions isn't bad. It just probably makes you feel more comfortable with whatever it is you're doing, even if it's always inverse cosine. Especially, all the double checking stuff I talked about. Not because how it's drawn. 8 is significantly smaller than 29. So I know that I'm expecting this side length to be significantly larger to compensate for that, which means this angle should be significantly larger than, 45 degrees. It shouldn't be in the teens or anything like last time. So inverse cosine of 8 over 29 will give me 73.9 degrees, so about 74 degrees. That would be to the nearest degree there, 74. And there we go, that's number 16. Number 17, find the area of each triangle to the nearest tenth. Okay, well, let's start off with two concepts here. First of all, the area of any triangle. It is 1/2 base times height. 1/2 base times height. Second thing is, if you have a scenario like this, a side angle side, the angle in between two known sides here, it is possible by finding the area of the triangle as well without needing to know a height perpendicular to a base length if you say that it's 1/2 times A times B times sine of C. Now, this is a formula that, look, I don't exercise this one enough, and I don't want to. I don't intend to. You'd have to understand what A and B are. C is actually an angle measure. C is the angle measure in between these two letters right here. I'll keep this open so you can see us do it a practical way and us getting the exact same answer almost every time. Plus, it emphasizes some other important things to know about sine, which I want to do. First thing I'm going to do is lay this thing down in one way so that, let's see, I'll put K here, H here, and P here. Reason I'm doing this is to note a base length that I want to choose, such as this one, 10.9. It's not that base has to be face down, but I kind of prefer it that way. I prefer to see my base on the bottom or top and my height going up and down, stuff like that. Speaking of which, your base length does have to be one of the side lengths here. This one, or if you use law of cosines, you can find out this one. So it does have to be one of them, like in general, just like as far as bases go. Height never does have to be one of the side lengths. What it does have to do is it has to be perpendicular to your base length, to your base, and it needs to reach its highest point. So for example, this altitude from P all the way down to the ground where the segment KH is formed can be represented as my height right here. And even though it's extended out from base, that's okay. It's still perpendicular to it. This distance is what we're looking for. So what we really want to know is what this length is by using some of the other things in here. Notice what I made is a right triangle. Well, I don't know any of these two angle measures here, or do I? This one right here happens to be 48 degrees because it's supplementary to 132. They both add to 180. Now, why does that matter? Well, I can take the sine of 48 now. See, I can take sine of 48, and that thing will be h, opposite, over 10, hypotenuse. H, 10. See, 10 is the right triangle, is the hypotenuse of the right triangle here. Multiply both sides by 10, and we get h is going to equal 10 times the sine of 48 degrees. Now, when I write out this formula here, by the way, base length, as I said, was 10.9. I'm choosing this as my base. When I write out the formula here for area is 1/2 base times height, I'm going to get area equals 1/2 base times height, 10 times sine of 48. So what if we did the same principle, because I'm not going to write this answer yet. What I want to do first is come up with writing it in this format as well to see if this was convincing enough to do. It honestly wasn't a lot of work, but that it was enough to do to make sense of it. Because what if instead I called this A, this B, and this angle measure C? Would I even be writing out the same stuff? So I could also write out the area of my triangle, let's see, as 1/2 A, I'm looking up here, times B times sine of angle C. So you're looking at these two and you're saying, well, clearly these aren't the same. Nothing really looks the same here. 1/2 looks like that. And this is times A. I'm going to do the top one first. Times A times B times sine of C. We're going to get this number here about 40.5. What do we have to round to? Nearest tenth. So about 40.5, not degrees, square kilometers. This is an area talking here. 40.5. Okay, there's one answer. Now, you might be trusting that formula or trusting what I wrote to be the formula here, but let's see if we get the same answer here. Okay, now I'm going to do the one in green here. 1/2 times 10.9 times 10 times sine, or just right sine of 48. And what do you know? Look, we get 40.5 again. So, now the questions become, what? Now the question really becomes, how did that happen? How is it these things are the same despite the fact that we didn't write the same thing? Like, it's one thing to say, oh, look, you rewrote it and it looks like the formula. This kind of looks like it. There's two numbers here and then whatever else. But these numbers are different. And these numbers are switched. And this doesn't have parentheses here. Well, let's break some of it down, especially the front. Number one, this has a 10. This has a 10.9. So those are the same. And multiplication is commutative, which means that you can maneuver these things around and get the same result. See, 10 times 10.9 is the same thing as 10.9 times 10. Whether or not I used a parenthesis here to really separate the facts, that I have something there. That's irrelevant, right? So this is still 10 times that amount. So that's number one. These things are actually the same, even if they're written differently. Number two, sine of 132 and sine of 48 are both the same number, because when you're looking in here, what you're referring to, by in here I'm referring to a set of axes here. 48 degrees goes 48 up from 0. Boom, right here. That's 48 up from 0. 132 goes over here, and the terminal side is 48 degrees up from 180. Right? These are supplementary. Well, all students take calculus. Sine values are positive here and in here in both quadrants. And remember, sine of 132 is the same as sine of this triangle. And it literally is because even the sine, S-I-G-N, even the sine is the same. So these are both the same thing, sine of 132 and sine of 48. So what's nice about these obtuse angles here is we can use the acute supplement counterpart, and you'll still get the same answer regardless. Right, so that's kind of nice moves with that thing. So anyway, this is a formula that can be used. You have to know how to use it, why to use it, when to use it. But I'm going to stick with this. I'm just going to stick with 1/2 base times height. It really talked about other things there. I guess I used this as an example to mention it. But, really good practical stuff there, especially with the obtuse triangle. That's number 17. Okay, number 18, we have triangle ABC here, and I'm going to do the same thing as before. I'm going to draw an altitude down to a base. Now this altitude is going to cut off the 79 a little bit. My apologies. Just remember that number is a 79 right here. I have a little tiny triangle right there where I can determine this height using sine of this angle measure, sine of A, 79, equaling h over 6.2 miles. So h can be re-represented as 6.2 times sine of 79 degrees here. Okay, now if I chose that as the height, obviously I chose the bottom here as the base. My base length here is 11 miles, so B is 11. And when I now calculate this stuff here, the area of the triangle, I'm going to be doing 1/2 base times height, which will round to whatever the calculator gives me. Oh, trust the calculator as much as you can, I guess. That's fine. 1/2 times base times height, sine of 79. Okay, around 33.47, so around 33.5. Okay, about 33.5. I always want to say degrees. Square miles. Okay, that's how much coverage we're referring to right there. Pretty nifty. Maybe it's like a city. I have no idea. Tri-county area. One more thing to mention before moving on. Notice how I chose this as height and this as base, right? Another question might be, well, what if you chose this as base and this as height? Draw the altitude and stuff. Hey, that's fine. It's just going to be different numbers, but that's fine. Now, the last question, well, actually, the numbers will technically be the same, just written differently. Last question is, what if I chose this as base and this as height? Well, here's the problem. Unless or until we use law of sines here, or law of cosines to find out this side length opposite it, you don't know any angle measure here or the base length here to do that with. So whenever I chose my altitude, I clearly made sure to choose an altitude with an angle I don't know to draw it down so that I could work it with an angle that I do know. Okay, so that was the important concept about that. So no matter what you do, you will get the same answer. You just got to figure out what approach you got to use is best. State the quadrant in which the terminal side of each angle lies. No calculator for me. Let's take it away. Negative 30 degrees. Now look, all we're answering, I'm just going to answer the question. All we're answering is what quadrant it's in. Okay, so I'll draw this a couple times. In fact, I'll group and copy and paste each time. Oh, not yet. Let's get rid of one of those. Negative 30 degrees. Remember, every time you start, 0 starts eastward, this way. Excuse me. So 30 degrees will go 30 down. I have the hiccups. 30 down. And right there, it's less than 90. We're in the fourth quadrant, quadrant 4. That's all we got to find there. So number 20, same idea here. Oh, I guess it didn't copy. That's all right. Do this one more time. This time, let's officially copy. Copy. Good. All right. Number 20, 140 degrees, and in the positive direction. So from 0, we're going to go up and past 90, not quite to 180. right? Who cares what the reference, I mean, it'll matter later. The reference angle, if you must know, this was an additional 50 from 90. So this reference angle here is 40. So that will matter later. But the point is we're in quadrant 2. That's the quadrant in which this thing lies. Nice. Number 21, we got negative 47 pi over 18. Okay, tough one there, right? Some people might look to convert to degrees immediately. And look, I'll get to degrees eventually. But what I really want to do is just figure out how many full revolutions have I gotten. Then the conversion will be a lot easier. Or the understanding of where I'm at will be significantly easier. So 18, if you divide by 18, the top can be 36. That'll give me 2 pi. I'll make sure it's negative. And then minus again, the remaining amount is 11 pi right there over 18. So this is a full revolution. I'm just going to ignore that right now. We did a full 360. We're back to where we were. Negative 11 pi over 18. You know, some people might look to convert that to degrees. If you must know, pi is 180 divided by 18 is 10 times 11 is 110. So we'd go 110 in the clockwise direction. If you didn't know that, here's what you do have to know. Pi is 180, so 11/18 is less than 1. I know the answer will be less than 180. The only question now is it more than 90? Well, pi over 2 is 90, and that would be 9 over 18, right? So this is a little more than 90 in that direction, and not quite 180. So it's probably landing about there. One full revolution, and then going around here past 90, landing there. That is quadrant number 3. Again, calculator-free math and understanding there is really what we're going for. Number 22, last one, 4 pi over 3. I think we already answered one of these questions for what the actual degree measure is. This time, let's play with the degree measure. Let's, I'm not even going to draw. I can ignore that drawing. 4 pi over 3 is 4/60. Okay. Actually, no. Here, let's go to the drawing. Besides just 240, maybe you don't know which angle that's in. So try 4/60 instead. 60, 120, 180. All right, 240. Okay, quadrant 3. We're good. Right, so sometimes it's just a matter of where am I at, what do I got? But make sure, and terminal side is just the place where it ends. Just make sure you know what you're answering. Number 23, find a positive and negative coterminal angle for each given angle. Starting with 23. First of all, positive and negative coterminal. Coterminal means landing in the same place as this angle does. For example, negative 20 is whereabouts, like right here, okay? 20 down. What we got to find out is negative 20. What we got to find out is if I do a full revolution, what angle measure am I at now? By the way, that's not a 120, that's an arc symbol. What angle am I at now? And a full revolution from negative 20 is adding 360 to that number. Plus 360 gives me positive 340 degrees. This is one of your coterminal angles, and it happens to check off our positive question there. Okay, landing in the same spot. And negative coterminal, negative 20, let's subtract 360. Let's go full revolution backward like that, and we land on negative 380 degrees. Now, the point of coterminality allows us to do a few things, specifically regarding trig. If I take the sine of negative 20, for example, that's the same thing as taking the sine of 340 or the sine of negative 380. Same exact reference angle and same quadrant. And that's really what we're referring to there. So that answers those questions, and that's just 2 answers. As it asked in degrees, I'll answer in degrees. Later for 25 and 27, I'll answer, 25 and 26, I'll answer in radians. The other thing is make sure one's positive, one's negative, and they are different from that answer. Look, I could add another 360, but I won't. I'm going to stay right there. It's good enough. Number 24, negative 146 degrees. Okay, let's go ahead and place it in again and just make sure we know where we're at. You know, I won't draw these anymore after this. Negative, it goes down. It's not quite at 180, so we know it's third quadrant stuff here. Okay, where exactly? I don't know. It's all right. We could say, okay, negative 146 from 180 is, oh boy, 34 degree reference angle there. So one other way I could do it besides adding 360, you know what I could do is take 180 and add 34. That'd be 214. Okay, so 214, see if that number is going to work out as my answer. Negative 146 plus 360. 360 minus 146. Any takers? All right, it's 214. So that's one of our answers there. The other one, I guess, that we have to do from there is subtract 360 from 146. That's going to be about negative 506 degrees. Negative 5, or not about, exactly, negative 506 degrees there. Coterminality comes in many forms there. Look, the drawing for these kind of don't matter. The first explanation was good. I like the reference angle bit about 214. Here on out, I don't think the drawings will be necessary. Number 25, negative 17 pi over 18, coterminal to this one. And as I said back on number 23, I'm going to answer this question in radians. Now, what I'll see some people do with these problems is they'll convert this to degrees, then find coterminal angles, then convert them back into radians. And by all means, look, do it if it's comfortable to you. What I'm going to do is I'm just going to add and subtract 360. Well, 360 in radians is 2 pi. So I got to find out what this is when divided by 18. Well, that's going to be 36 over 18. So I'm going to add 36 over 18, 36 pi over 18. And I'm also going to subtract 36 pi over 18. And that will give me two coterminal angles here. 36 pi over 18. So adding it, 36 minus 17 is 19. So that'll be 19 pi divided by 18 right there. That's one of my answers there. That answer is a little more than 180 degrees. Actually, it's 190 degrees, right? But I want my answer in radians. Next one here, 17 plus 36, so that's 53. So this will be a negative 53 pi over 18. And look, as long as you might ask, can this reduce? Because, yeah, I'd expect a reduced answer. Can this reduce? No. If this could reduce and this couldn't with the same denominator, no, we're not looking at something that can reduce there either. So there's 25. 26 is going to be the same thing. We're going to add and subtract 2 pi here from these numbers. Now 2 pi in terms of this here, that's 72 pi divided by 36. So 5 pi over 36 plus 72 pi over 36 is going to give me 77 pi over 36. Also cannot reduce for the same reason as I mentioned from the previous problem. One of them could, this one can't, so this can't. Okay, the next one here, 5 pi over 36 minus 72 pi over 36, 72 pi over 36. That's going to be, what, negative 67, I guess? 72 minus 5 is 67. So negative 67 pi over 36, also coterminal. What are those angles in degrees? I don't know, divide by 36 and go to work. There you go. They're coterminal, they're positive, they're negative. That's what we're looking for. We know when we do sine and cosine of that stuff, right? Those are the angles that we get. Number 27 through 34, we're going to find the exact value of each trigonometric function. Yeah, we are. And those answers normally tend to be fractions, or they have radicals, or -1, or 0, or stuff like that, or undefined. All right, we can divide by 0 and have undefined. Let's start with 27, which actually is not the easiest problem of the bunch because most of these things that I'm going to draw here have to do with drawing special triangles. Now, this triangle will be very special in that it won't be a triangle, but let's pretend like it was. 180 degrees negative goes like that, and it lands here. As you know, for most things, I like to build right triangles, meaning I draw it like this, right? Draw something here, here's your reference angle, stuff like that. Problem with 180 is it's right on the x-axis here, on the negative x-axis. So let's think of it like this. Let's talk about it like limits. The limit as x approaches negative 180, or theta approaches negative 180, right, means that your opposite side is approaching 0, and your adjacent side is approaching something that's equal to your hypotenuse. They'll be one the same, sort of. See, adjacent has the ability to be negative as long as I'm going left. Hypotenuse does not have direction in terms left and right. It's clockwise, counterclockwise. So we just call it what it is. It's just a magnitude right there, 1. So when we do cosine of this reference angle right here, that'll be adjacent divided by hypotenuse, -1 over 1, which is -1, and that's our answer. Okay, a second way you can do this is if you do know, pretend like that's a axis, is if you do know your cosine graph, and it's looking like this right here, okay, it starts at 0, 1 right there, but if you go to negative pi, it's going down to negative 1 right there, and that's your answer as well. Okay, so if you know your graphs, that'll work just fine too. That'll do. But otherwise, the triangles is going to be, the triangles will be my focus as long as I'm doing these kinds of problems like this right here. Number 28, cotangent of 690 degrees. Okay, this goes back to that coterminality concept. Cotangent of 690 would be equal to the cotangent of a coterminal angle that's between 0 and 360 here. And that's exactly what I intend to find. Okay, so 690, you could subtract 360 to figure out what that angle is. I'm going to go a little different. I happen to know that 720 is 2 full revolutions. It's 2 360s. 360, 720. That gets me back to 0 right here. So that's 720 degrees. Okay, well, how much lower is 690 than 720? Well, it's 30 degrees lower. So if I subtract 30 right here, guess where I'm at? Right there. And I don't care what the actual angle is, 330 degrees. But this is also 30 away from 360, 720, and 0. So there's a 30-degree reference angle right there. That's the most important part of this, the 30-degree reference angle. Okay, and that has a certain ratio relationship within its triangle. Opposite 30 is a 1, its hypotenuse is 2, and the adjacent side is root 3, where 1 will be negative because we're going downward. So if I want to take the cotangent of this guy right here, of negative 30 or what have you, this will be adjacent over opposite, right? Tangent's opposite over adjacent. This will be adjacent over opposite right here, which is negative root 3. Now, if you forget to have the negative sign right here, another time you can save yourself, even if you made it positive, is all students take calculus, ASTC, where only cosine and secant are positive ratios here. Tangent and cotangent aren't positive in the fourth quadrant. So you could know to write a negative answer there, even if you had the one positive to begin with. Okay. Regardless, though, it should give you negative root 3. Number 29, cotangent of negative 630 degrees. So kind of the same stuff. Two differences. One is the angle, and one is the sine of the angle. So negative 630 right here, let's think of that 2 full revolutions thing I said last time. 1 full revolution in the negative direction is 360. 2 full revolutions in this direction here is 720. And 630 is 90 less than 720, so I'm going to subtract negative 90, which is adding 90 right here. And we're going to end up right here vertically on the positive y-axis. Okay. So how do we take the cotangent of that? Well, we can do what I talked about last time, perceive this thing instead like a right triangle, just a skinny one. I'll do it on this side just to give myself some room. Skinny old right triangle right there where it's getting so close to this guy right here that it might as well be it, which means if this is your reference angle here, adjacent to it will squish to 0, opposite it will raise to be the exact same number as the hypotenuse. If this is 1, this is 1, this is 1 as well. Okay, so cotangent is adjacent over opposite. Well, the adjacent side to theta here is 0. The opposite side here is 1. 0 over 1 will give us 0. And that's it. Number 30, tangent of 135 degrees. Okay, well, 135, if we place that here, that's 45 up from 180, right? Here's 45 up from 180. Boom. That's 135. In a 45, 45, 90 triangle, the ratio relationship is 1 to 1 to root 2. This one is negative as it goes to the left. This one stays positive as it goes up. Tangent is opposite over adjacent. So positive 1 divided by negative 1, your result's negative 1. Number 31, sine of 13 pi over 4. This number looks a little less, doable as far as calculations and such. So what we can do is what we did before. See this as a little more than 360, right? A little more than 2 pi. 2 pi here will be 8 pi over 4. So what's remaining is the 5 pi over 4 here. So again, this is where like 8 pi over 4 can kind of be ignored because sine of 5 pi over 4 is the same answer as sine of 13 pi over 4 because these are coterminal. So get this out of the way. 5 pi over 4 is 5 45s. or it's 1 pi over 4 more than pi, right? Because that's 4 pi over 4. 225 degrees. That is a third quadrant guy. That's 45 under 180, down from 180 right here. That ratio relationship, again, is 1 to 1 to root 2, where the ones are both negative as they go left and down. And we're at sine here. So sine of this guy here, opposite, let me write it down below. Sine of 13 pi over 4, or sine of 5 pi over 4, is opposite, which is negative 1, over hypotenuse, which is square root of 2. And ordinarily, this would be a fine answer, except let's rationalize our denominator by multiplying top and bottom by root 2. We'll get negative root 2 over 2. There's your exact answer value of the trig function right there. Number 32, tangent of negative pi over 3. Okay, well, negative pi over 3 is negative 60. So tangent of negative 60, we'll be going 60 down from 180, so down, or excuse me, from 0, which is down right here. The reference angle is 60. Opposite 60 is a root 3, where it's adjacent 1, it's hypotenuse 2. 1 to 2 to root 3. Root 3 is negative as we go downward. Tangents opposite over adjacent, negative root 3 over 1, that is negative root 3. Number 33, sine of negative 17 pi over 6. Kind of the same thing as number 31 from above here. It's a little more than 360, and it's probably best that we determine what it is based on that analysis. So that would be equivalent to, so negative 17 pi over 6 is also negative 12 pi over 6. Again, that's a full 2 pi, full 360, minus 5 pi over 6. I think we used this number before, didn't we? Negative 12 pi over 6 can be obsolete there. We did a full 360. We're back at 0. Negative 5 pi over 6, that's negative 5/30s. That's negative 150. Okay, negative 150. I'm going to go 150 in this direction here, and I'm going to land 30 under 180. Or at least, you know, reference angle is 30. That's the important part. Reference angle is 30. Ratio relationship 1 to 2 to root 3. The 1 and the root 3 are both negative as they go left and down in the third quadrant. Sine of this guy opposite over hypotenuse is negative 1/2. Negative 1/2. Negative 0.5 is also an exact number. I will acknowledge that. And you can test that in your calculator. Make sure you're in radians mode, and you'll get negative 0.5 as an answer. Finally, cosecant of pi over 6. Last time, pi over 6 is 30 degrees. So we'll just go 30 up from 180. It looks like one kind of from hardest to easiest in a way. Pi over 6 is 30 degrees here. This is a 1 to 2 to root 3. One more time. And by the way, just to make mention, 2 is more than root 3, right? Because 2 is root 4. So 2 is the hypotenuse in this case. It is not root 3. And as 30 is less than 60, then 1 is less than root 3 as its opposite. I do not want you to get those ones wrong when it comes to marking them, of course. Cosecant is the reciprocal of sine. Sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite. That's 2 over 1, which is 2. There are the exact values of the trig functions. Okay, number 35, use the angle, sum, or difference identity to find the exact value of each thing here. So what we're going to look to do in a problem like this is 75 is not a special right triangle of any sort, but what it is it's a culmination of some special right triangle angles that we know, such as 45 and 30. Now, if only it were so easy as to say that we just distribute the cosine into both of these. Unfortunately, when you take the cosine of two different angles, I'll call them u and v, as you would probably see in your textbook there. It's cosine, cosine, sine, sine, meaning cosine of these two multiplied together, separated, that's a v. And then a minus, if this is plus, for cosine it's actually minus here, minus sine, sine, sine u, sine v. So in this particular case here, as I substitute these things in, that'd be cosine of 45 times cosine of 30 minus sine of 45 times sine of 30. Okay? So cosine of 45, let's build some triangles here really quickly, just so you have the idea. I don't want you to get it wrong. 45, 90 is 1 to 1 to root 2. And 30, in 30, 60, 90, 30 is 1 to 2 to root 3. Okay, cosine of 45 here. That's 1 over root 2, which is root 2 over 2. And I'll multiply root 2 over 2 with cosine of 30, which is root 3 over 2. So root 2 over 2 times root 3 over 2 will be those two. Sine of 45, like cosine, is also root 2 over 2. The same angle. Sine of 30 here is going to be 1/2. 1/2. Multiply and subtract. Root 2 times root 3 is root 6. This is over 4. Minus root 2 times 1 is root 2 over 4. As they are a common denominator here, I'm going to write them both right next to each other, root 6 minus root 2 all over 4. That'll be as simplified as we can really get in terms of exact values. Do they ask for exact? Exact value of each here. So here's an exact value. I can't simplify this stuff up here. It's not like the root 2 can subtract into root 4 or anything like that. No, this is just how the answer would be written with a common denominator there. And that's really all you have to do. There are probably other angle measures we can find. These are the two simplest ones I wanted to work with there, and I do not regret using those two. Okay, sine of 165. Now we're going to be using a sine sum formula here. And for sine, you have to come up with two numbers here that we can add together that we know. They don't have to be first quadrant angles, So I also know that I can use 135 because that's 3 45s. Meaning I know how to find that ratio by hand. That's the point. And I can add 30 to that one, and as we know how 30 works, we'll do that again. So let's go ahead and figure out how 135 is going to work with this, and I'll write out my sine double or sum angle formula here with you in just a moment. If this is 135 going out that way, then this is a 45-degree reference angle right here, obviously not drawn to scale. 1 to 1 to root 2 would be that relationship right there. I'll make sure to use that when needed. And this is 30 degrees right here, and as we saw last time, 30 degrees has a 1 to 2 to root 3 relationship as follows. Now the sine formula, when you're adding two guys right here, that's u plus v, it's sine, cosine, cosine, sine. Sine, cosine, and sine happens to be separated by a plus when adding. Plus cosine of the other times sine of the other. Sine, cosine, cosine, sine, cosine, cosine, sine, sine. That never leaves you whenever you actually learn it and do it a lot. Because, look, I haven't used it in like 15 years. Okay, so sine of 135 plus 30. We're going to be doing sine of 135 times cosine of 30 plus cosine of 135 times sine of 30. Whoops, whatever. Sine of 30. Boom. Okay, sine of 135 here. So inside 45, opposite over hypotenuse, that's going to be 1 over root 2, which is root 2 over 2. Cosine of 30 is root 3 over 2. So we're left with those. Okay, plus we'll do cosine of 135. Now, in all students here, cosine will be a negative answer. Whoops. All students take calculus. Cosine would be a negative answer here, and that makes sense. Negative 1 over root 2. It's negative root 2 over 2. Times sine of 30, that's 1/2. So our final result here, well, not final, but let's clean this up a little more. Root 2 times root 3 is root 6 over 4. Hey, that looks familiar. Plus a negative right there, and this is root 2 over 4. This looks very familiar. Looks a lot like the previous problem we did. Root 6 minus root 2 all over 4. That ends up being your final answer right there. No real connection that I know between this one and this one that tells me why these two answers were the same, or if this was intentional or coincidence that they happen to be the same, but they're the same. So those two, there you go. Use a double angle or half angle identity to find the exact value of each expression here. Cosine of theta is 12 over 13, and we're going to choose a theta that's between 270 and 360. That's quadrant number 4. Quadrant 4. We're going to find the tangent of 2 times theta. So this stuff is within this tangent right there, and let's go to work. First of all, the reason they specify quadrant 4 is because you can get positive 12 over 13 for cosine in two different quadrants. Quadrant 1 for all, or quadrant 4 for cosine. Or calculus. So the fact that they're specifying quadrant 4 is important because if we're going to find other trig functions, we need to know specifically which triangle to which we're referring to make that exact kind of thing happen. So 12 over 13, if we're going to do a theta in the fourth quadrant with 12 over 13, we're referring to our adjacent length here as 12. This guy is 12. 13 is the hypotenuse. So 13 coming out like this right here. There's another side length for which we probably need to find. I'll see if we do here. It looks like we do. And I'm going to call this my theta right here. They're saying that the placement of our reference angle is between 270 and 360. How about that? I think it's going to be important to figure out what this unknown value is here. I'm going to call it x because we're going to do things involving tangent, and that's opposite over adjacent. So with opposite here being x, it's crucial to know what x is here. So x squared plus 12 squared is 13 squared. I think we can agree. X squared plus 144 is 169. Subtract that, we get 25. And divide, we get, or square root, we get 5. Now, two things for this. Number one, this was a Pythagorean triple. It's a 5, 12, 13 special triangle. If you know that, more power to you. If you don't, do the Pythagorean theorem, you got it. Second thing is this 5 is not positive. It's actually negative because we are going downwards. And this is the exact reason why it's important to know what quadrant we're in. We could have had 12 over 13 up in the first quadrant just fine. That would have been cosine of theta as well, 12 over 13. But this 5 would have been positive. And that changes answers, as you can see. Tangent has a different opposite value now. So stressing there in quadrant 4 is their way of saying, make this 5 negative. Okay, the next part is the tangent of 2 theta. Now, this is a double angle formula. It's kind of a strange one, in fact, if I recall it correctly. Tangent of 2 theta would be 2 times tangent of theta all over all of 1 minus tangent squared of theta, like so. So what I'm going to do is determine what tangent of theta is and apply it in here, okay? And then I'll be able to find out what my exact answer is as a result. So tangent of theta in itself in our triangle is opposite over adjacent, negative 5/12. I'm going to use this negative 5/12 in this formula to be able to find out what the tangent of this 2 theta is right here. Notice this entire time I never bothered to figure out what angle theta was, and I could double check with the calculator that if I double that angle, the answer that I get would work out. The one thing about theta here you'd have to make sure of is that it's the theta that's in quadrant 4, not in quadrant 1. Because you take inverse cosine, you're going to get a quadrant 1 answer. Anyway, I digress. Let's go back to this problem here. So tangent of 2 theta of our 2 times our unknown angle that shall remain unknown, and it's not a special angle, by the way, is 2 times negative 5/12, right, tangent of theta, divided by 1 minus negative 5/12 quantity squared. Okay. It's kind of tricky stuff. We have fractions within fractions here. On top, I have 2, which is 2 over 1, times negative 5/12. 2 over 12 can reduce here. This can become a 6 as this becomes a 1. So this becomes negative 5/6 on top, negative 5 over 6. On bottom, I'm going to be doing 1 minus negative 5 squared is 25. Excuse me, and 12 squared is 144. Now, this became positive as I squared it. I'm still going to be subtracting it though. Okay, so that end result there, I still subtract because that was a negative on the outside of the quantity. My apologies, hiccups running rampant right now. All right, so on the bottom, there's some cleaning up to do here. We have a common denominator issue, or a lack thereof common denominator. 1 is 144 over 144. So if I subtract 25 from there, it looks like we're getting about, or exactly 119. So 119 over 144 we do have on bottom. So here I got negative 5/6 on top. You know what, this is better here. If I write it left to right. Divided by 119 over 144. Reason for this is not to have the fraction over fraction nonsense, and this is kind of how we can compute it. Multiply this by its reciprocal, times 144 over 119. Now, I'm still not about to whip out the calculator here. My end goal is to do this without it. And no, I'm not about to multiply these two together and reduce. No, what I'm about to do is see what can reduce. 144 Yeah, 144 can divide by 6, not just divide by 2. We can divide by 6. 144 divided by 6 is 24. Okay, a lot of different ways it could answer that one. That's 20. 6 times 20 is 120. 6 times 4 is 24. 120 plus 24 is 144. So this can be 24. This can be 1. And now it's a much more reasonably easier to multiply thing right there. That's going to become, remember, this is all tangent of 2 theta here. So tangent of 2 theta, that's pretty thick marker. Tangent of 2 theta there, negative 5 times 24 is negative 120 over 119. That ratio right there. It's extremely close to 1. Okay. Now, just to be that person, because I know the answer key probably says that answer here, but just to be that person who you want to be to double check your work if it comes to a test, kind of something like that. Okay. Let's do this. Let's find out what the exact angle measure is by taking the inverse cosine of 12 over 13. Now remember, the answer that we're going to get here is a degree measure that is between 0 and 90. It's that one right there. If you want to figure out what the exact angle measure is right here in space, you got to be talking about 360 minus this number. Okay, if you truly want to be referring to the number that we're going to be taking the tangent of 2 theta with, this is our angle measure that we're actually taking the tangent of 2 theta with, believe it or not. So when I take the tangent of 2 times our previous answer right here, our result is going to be this one, negative 1.008. Well, what do you think negative 120 over 119 is? It's that number. Okay. Now, I do wonder if going back to that previous work, if I went to fraction, maybe it would give me this answer here, the fraction button right here. I guess it should, because I computed that. So, hey, that's one way to cheat it, I guess, if you use a calculator, if calculator is allowed in a section like that. But that's just a nice double-checking work thing with that. You know, the formula is one thing, then doing it right's another, knowing where you're at. So that's problem number 37 there in a nutshell. Okay, problem number 38, we have cosine of 4/5, and then we're in fourth quadrant again. So Q4. If I paste, yes, I still have this again. We're gonna find sine of 2 theta. Okay, so here 4/5, fourth quadrant. That's 4 as an adjacent, 5 as a hypotenuse. Okay, and we got to, especially with sine here, we're gonna have to find out opposite. So 4 and 5. Now, as the last one was a 5, 12, 13 special right triangle, this is a 3, 4, 5 special right triangle. But do not forget that there should be a negative there. Again, fourth quadrant does affect sine just like it affected tangent. We expect it to at the very least. So find sine of 2 theta here. Well, sine of any 2 theta in general, think of sine of theta plus theta, right? In terms of the sum formula. That's sine, cosine, cosine, sine. But of the same angle, that's 2 sines and cosines together. 2 times sine of theta times cosine of theta. So without actually knowing what the angle measure is, what we can do is figure out what sine of this particular angle measure is. Looks like it's going to be opposite, negative 3 over hypotenuse 5. And then cosine of this particular angle here is positive 4/5. So I'm going to use these numbers here in this formula, kind of make everything click for me here. So sine of 2 theta will be 2 times sine of theta times cosine of theta. Probably an easier problem than the last one. This is 2 over 1, by the way. 2 times negative 3 is negative 6 times 4 is negative 24 divided by 5 times 5 here is 25. So there's your answer here. I guess negative 0.96 as another answer, as an alternative, because that's exact there. You can use one or the other, and you can use the calculator to double check like we did for problem number 37. But this should be your answer here given this sine formula and this quadrant in that ratio. Number 39 through 42, we're going to solve each equation for between 0 and 360 degrees, every single theta value we can obtain. Now understand that as they say 0 to 360, that means a couple things. Number one, only between 0 and 360. Number two, if you get an answer of 0, only write 0 as your answer, not 360, because 360 is not included in the domain. And number three, our answers, yes, are written in degrees, Not because of the symbols I put overhead, but because of the numbers that they gave you. I think that's a fair assumption to make, that this is not a radians answer, and if it was, you'd have a lot of answers to be writing. Probably nearly, I don't know, like 100, I don't know, just dozens. Several. Very much. Okay, so solve for theta here. The whole end goal is to get the trig function by itself. Like in this case here, for number 39, I'm going to subtract 1 over. Tangent of theta is 1. Okay, so now I got to take the inverse tangent of both sides here. Theta is the inverse tangent of 1. And I don't really know if that answers your question there, because without a calculator, this is still achievable. What you really want to say, besides this step here, is let's go back to this one for a moment, because this really only helps me in the calculator. In this one here, I'm asking myself, what angle do I take the tangent of to get the ratio of 1 over 1? Okay, that's the real question that's being asked here. So what I like to do for these problems is, first I like to build out a right triangle and decide if I can figure out what the degree is then and there. In this case here, if you have theta and your opposite is 1 and your adjacent is 1, you might have recognition of the fact that this is a root 2. If you don't, use Pythagorean theorem, and once you do that, by that point, hopefully you can recognize, hey, this is a 45-degree angle measure here. Theta is 45. Now, is that the answer to the question? Maybe. It's part of it. The question is, what are all the angles here that satisfy that one? And yes, it's a positive one. We are probably going to see some that have negative ratios, and you'll see I will still build this first. Then I will go to this guy right here. And what my plan now here is to take the 45-degree triangle like this and build it as a reference angle everywhere that tangent is positive. Tangent's positive in first quadrant, 45. In this quadrant, third quadrant, 45. Now I get to answer the question, between 0 and 360 and the length of one full unit circle, what does theta equal? Well, 45 is one of my answers right here. I'm going right there, 45 degrees. The second answer here is 90, 180, 225 degrees. That's how far it has to go. And try it in your calculator. Do 1 plus tangent of 225. You'll get an answer of 2, assuming you're in degrees. But that's your final set of answers there. Those are the only two that land in between there. Because they asked for degrees I gave. In radians, this would be pi over 4 and 5 pi over 4. Number 40, 6 times sine of theta equals 3 root 2. Okay, divide by 6 to isolate sine of theta to begin with. Sine of theta will be 3 root 2 over 6. Strange ratio, you might say. However, 3 over 6 reduces to 1 over 2. So this is root 2 over 2 right here. So the question remains the same as last time. In what kind of triangle can I take the sine of such an angle theta and get a ratio that is root 2 over 2? So I'm going to show you this to begin with. Root 2 and 2 here. You're saying, gee, we haven't learned one like that. And by all means, right now you might say, I really have no idea. Here are some things you can do. Number one, you can use Pythagorean theorem to figure out what this length is here. If you use Pythagorean theorem, you'll find out that answer is root 2. In which case, you might be able to find a connection here. Hey, these are the same, which means I'd have to multiply by 1 to get from one or the other. And over here, I have to multiply by root 2. And here, I have to multiply by root 2 to get this number. This is equivalent to a triangle like 1 to 1 to root 2. Has the same kind of thing. So one thing you can do is figure out by proportional similarity of triangles and such that this is also a 45, 45, 90 triangle like this one is, but it's just root 2 times larger everywhere. A second way you can do it is understanding the fact that we normally get root 2 over 2 by rationalizing the denominator of a previous fraction. And that previous fraction is 1 over root 2. So what I'm generally going to do for these problems here is take the rationalized denominator version of a number, de-rationalize it, meaning make it an irrationalize it and make it back to where it was and just draw that triangle out because I know what this one is here. That theta is 45 degrees. Okay. So now the question becomes here, sine of this is positive root 2 over 2. So where do I build this 45 inside this guy right here? Well, for positive, we're going to use quadrant 1 and quadrant 2. See, 3 and 4, I'll get a negative sign value. Quadrants 1 and 2, I get a positive sign value. So here, we'll build it out, 45 and 45. Pardon my computer handwriting there. And so those two actual angle measures, the first one, as you can see, is 45 degrees, just like that previous problem. This one here is 45 up from 180. That's 135 degrees. So your two answers for number 40 will be 45 degrees and 135 degrees. Those two satisfy this statement here and therefore satisfy this statement way up here. Number 41, 4 equals 4 times the cosine of theta. Divide by 4, it looks like cosine of theta is 1. So the question is, what angle or angles here can we take the cosine of to get 1, or a ratio of 1 over 1? Well, if you have a ratio where the adjacent and the hypotenuse are the same length, hopefully it's you who can recognize that you're looking at a quadrant angle of some sort. You're either looking at, whoops, not V. You're either looking at 0, 180, 0, 90, 180, or 270. Or 360, which is 0 again, of course. So that's one way of taking a look at it here. So as far as quadrant angles go, again, build it out and consider, do I close up here, adjacent over hypotenuse, adjacent over, it's actually going to be this one down here. See, let's build it out just a little bit to make sense of it here. First of all, it's a positive ratio. Second of all, adjacent and hypotenuse match, which means this closes to 0 opposite, but adjacent is positive 1 going to the right. Here's hypotenuse. This angle right here has to be 0 degrees for this to work. So theta is 0 degrees. Now, does 180 work? Well, no, because 180 here has an adjacent side of negative 1. The hypotenuse will still be a positive 1. Cosine of theta would be negative 1 in that case. Another way of doing this, of course, is building out a, one of the periodic functions here for cosine. I remember drawing this before for you, but let's look at it again. Remember how cosine starts. Cosine of 0 is 1. Cosine of 0 is 1. 0 degrees or 0 radians. There it is. It doesn't go up to 1 again until another 2 pi or 360 degrees. And within this domain, we're not including 360 as an answer, just 0. So this is the only time we get 1. Negative 1 occurs at pi or 180. Number 42, 2 times sine of theta is negative root 2. So divide by 2, we'll get sine of theta equals negative root 2 over 2. And if I irrationalize it, I like to say derationalize more in this case. If I derationalize it right here, it would be negative 1 over root 2. So what I'm going to focus on here, I'm going to ignore the negative for a moment. I'm going to go back and ask yourself, you might already know the answer, what kind of triangle this is to get such a ratio. So 1 and root 2 go here if theta's here. And as you know, this would be a 1, which means this would be a 45. So we got another 45-degree triangle here. But look, now we're dealing with a negative. So the only difference I'm going to do here is when building 45-degree reference angles inside my unit circle, if you will, is with all students take calculus, I want to refer to, not all students, but take calculus. I want all my students to take calculus, of course. But 45 degrees right here and 45 degrees right here give us that negative root 2 over 2 ratio or relationship. That's why we build them there. The actual degrees for those between 0 and 360, let's go out 90, 180, 225. So one of the answers is theta equals 225 degrees. The second one, I could go all the way around here, or I could just subtract 45 from 360. That would be 315 degrees. So this one is 315 in the fourth quadrant. So 225 degrees and 350 degrees, those 315 degrees, those are the answers for number 42 that satisfy that one. Okay, numbers 43 and 44. Find the area of each triangle to the nearest tenth. Okay, as we dealt with the previous problems with area of triangle is 1/2 base times height. 1/2 base times height. And we also use that 1/2 AB times sine of C. Now, that 1/2 AB times sine of C would work if we knew a C value. And C in that case is an angle measure, not a side length. Of course, we use X and Y and Z here, and it's like, whoa, what do we do? So, look, we can't use 1/2 AB times sine of C unless we know an angle measure. And there's another thing called Heron's formula, which is kind of way out there. I'm not saying it's something you shouldn't use, but look, we haven't used it here. If you want to, go ahead and Google Heron's formula. Take a look and see if you can get the same answer. It is almost equally as complex as what we're about to do here. All the fraction stuff you have to do within a square root is mind-boggling. So, but what I'm going to do here is just some trig, okay? And I'm going to exercise something that we do have to practice, which is law of cosines. If we have our 3 side lengths known, we can find one of the angle measures of this thing here. Say like angle z, okay? By this is side length z, by the way, opposite. This is side length x. This is side length y. The cosine of angle z will equal little x squared plus y squared minus z squared over 2 times x times y. These are all side length measures here. This is the one angle right here. So cosine of angle z, of which we still do not know here, will be x squared, that's 12 squared, plus 9.9 squared minus 8 squared, all divided by 2 times 12 times 9.9. Clearly, we're going to have to do some calculator work here when we solve this entire thing. Okay, now by the way, what I'm doing here is I'm getting an angle measure so I can do what I did last time. I know I'm taking a break here for a moment. What I'm attempting to do is I'll use 9.9 as my base, okay, and I'll use my height as this altitude right here. So my end goal is to get an angle measure here that I can take the sine of, say, to get h over 12, right, this right triangle here. What I can't do, by the way, I know some people might say, hey, use 9.9 right here, but we don't know how long this is. See, so that's the issue. So we have to get an angle measure first to make all of this stuff, all the stuff work. Even the proof for Heron's formula uses law of cosines and sine and all the sine stuff. So no avoiding it. All right, so cosine of z once again. Let's use the calculator now. Let's bring that into play. I need it. I don't know what 9.9 squared is, to be honest. Okay, 12 squared is 144. I do know that one. So I got 12 squared, 144. I'll be plussing 9 squared. I'll be subtracting 8 squared, which is 64. On bottom here, I got to get those numbers too. So 2 times 12 is 24 times 9.9. Let's start with the bottom. 24 times 9.9 will give me 237.6. Okay, keep that in mind. And 9.9 squared looks like it's 98.01. So here we go. 98.01 right here. On bottom, we have 237.6. All right, subtracting all this here. 144 minus 64 is 80. So 80 plus 98.1 should be, excuse me, hiccups, 178.01. So cosine of z is 178.01 divided by 237.6. Okay, now to solve for z here, it's all about inverse cosine. There is no rhyme or reason to reduce this fraction any more than it could. To be honest, I doubt it could. So I'm just going to leave it like that there. So let's take the inverse cosine of this. Now, look. We're going to get an angle measure right here. Make sure you're in degrees when you do it. And whatever the number is going to end up being, I'm sure it's not going to be a pretty one. I don't trust this to be very pretty because I'm trying to choose the z value out of something you're probably supposed to do with Heron's formula. So I'm just going to write an approximate answer here. And for the calculator, I'll just make sure to store that answer as it's supposed to be. So inverse cosine of 178.01 divided by 237.6 will give me this angle measure of 41.47 degrees. So it's around 41 degrees, right? I'll just put 41 as I write it. Okay, so that's 41 degrees there. Now, what I'm going to do in the calculator is I'm going to make sure that I keep this number exactly as I want it to. I have a storage button here. Let's store it into, how about z? Store it into z right there. So that way I can recall z when I need to use it for my area formula when I'm solving for my height. Okay, so my height's about, not my height, my angle's about 41 degrees right there. I still need to find h in this scenario right here. So let's just write this as 41, even though I know it's not. We're going to calculate it differently. So what we're going to do here is use sine as we normally would. The sine of angle z, which is 41, is going to equal h over 12, right? opposite over hypotenuse. So your height is 12 times sine of 41. And of course, it's really not 41, it's something else. We're going to get it kind of exactly as we need to. So area is 1/2 base times height. If my base is 9.9, I'm going to be doing the area of my triangle as 1/2 base times height. This should give me the area in the end that I'm looking for. So let's go ahead and compute that. And again, for 41, I'm going to be using this letter Z right here. I won't be using 41 exactly. I'm sure the answers wouldn't be too far different otherwise. 9.9 times 12 times sine of Z, alpha Z right there. This gives us our full answer of 39.343 to blah, blah, blah. So rounding to the nearest, what do we say, 10th? Rounding to the nearest 10th here, the area of my triangle is approximately 39.3 square units. What do we got? Miles? Inches. Square inches. I think square miles is a much different answer. 39.3 square inches approximately. That solves it there. And look, you might argue that's a lot of work, but hey, we've done a lot of cosines before. It's not like that's out of the ordinary. And we've done this other stuff before. It really is a cinch. The question is, can you maintain your values and just follow along from there? Okay, number 44 actually is conventionally significantly easier than the previous problem we had there because we are looking at an angle measure this time, and we can do what we did previously. So we can draw an altitude. Just to be different, I'm going to draw the altitude this way this time to let you know that if I determine this to be height perpendicular to my base, that means my base is 10. This is my base length now. My height is this way. So now if you tilt your head left so the F is facing upward, and I'm trying to do it right here, I have this as a leg, this as a leg, this as hypotenuse. Just be different there, and by all means, do it this way if you'd like to. Draw your altitude there. We should get the same answer. We should get the same writing. The sine of 78 degrees for me to get my height here is going to be h over 12.1. So h is 12.1, 12.1 times the sine of 78 degrees. Okay? My base that I'm using is 10. So my area of my triangle here will be 1/2 base times height. That's 10 times 12.1 times sine of 78. Look, if you did it the other way, you know what would be switched is the 10 and the 12.1. But 10 times 12.1 is still 121. It doesn't change that for that part of the area. So let's approximate it, rounding it to the nearest 10th here. In fact, half of 121 is 65.5. Let's see if I can get the right answer here. I trust myself that I just did that correctly. Oh, that would have been 131. So 60.5. See, shouldn't trust that. 60.5 times sine of 78. Whoops, where's sine? Sine of 78 should get me the same answer as what you would be getting the other way. 59.2 degrees. Sorry, not degrees. What is this? Centimeters, square centimeters? 59.2 square centimeters. We're getting that answer for area of triangle. Assuming I typed the stuff right, I took half of 121. That was 60.5. That should be good. Okay, numbers 45 and 46. Solve each triangle, round your answers to the nearest 10th. Solve each triangle means find out every missing piece of information sans the area. So basically, in this case, we have all three sides. We got to find the missing angle measures. Boom, ba-da-boom, ba-da-boom. Okay. Now, in order to do this, let's do it quite like we did for problem number 43 here. Let's use law of cosines to find one of the missing angle measures, and then we have a lot of different options we can go to find the other ones. I'll just round this to the nearest 10th, but I'll use the exact answers here to calculate just in case. Okay, I'm going to use law of cosines, and what I'm actually going to do is use law of cosines on C first. There's a particular reason for this. C is the biggest angle here. When I take inverse cosine of something, I will be getting an answer between 0 and 180. Okay, and let's see. Well, hang on. I can't write and say this at the same time, so let me quickly call this A, B, and C. Okay, now what was I going to say? Okay, so I was going to say, so A squared plus B squared minus C squared over 2AB. Inverse cosine gives you something between 0 and 180. See, but if I choose to do let's say I find angle B first. Okay. If I find angle B first, and then later I say, I want to use law of sines to find angle C. Well, inverse sine, if you're going to use law of sines, that means you're going to use inverse sine. Inverse sine does not, repeat, does not give you any answers between 90 and 180. It doesn't give you obtuse angles. So my goal right here that I'm about to do is I'm going to be giving myself the possibility that this angle here is obtuse. Okay, this angle might possibly be obtuse. And according to the drawing, it is. I don't know if that's true or not. But I'm going to see if it is, because if it is, this is my only shot at checking that one. I don't know what 29 squared is. Well, 30 squared is 900. Let's go without a calculator for a moment. 30 squared is 900. Minus 30 is 870. Minus 29 is 841. So let's see, 29 squared, 841. Got it. Okay. See, this is something you want to do every so often as well. Test your own mind to see what your limitations are and what you can do from there. For example, I'm about to try, how about 34 times 21? 2 times 17 is 34. 34 times 20 is 680, plus another 34 is 714. Let's try that. What did I say, 714? Babe Ruth. That's how many home runs he hit in his career. Babe Ruth. There we go, 714. No, it is not, excuse me. No, it is not me showing off. It is personally stretching your boundaries, like this one once again right here. 441 plus 289. Okay, that'll be 730. 730 minus 841. Negative 114, or excuse me, negative 111. Okay, last time I'll do something like that if I have the calculator already out. Sorry about that. Time to time, that's something I have to do for myself. I'm not saying I'm doing it for you. I have to do it for myself. Whoops, I don't want to do that. I want to make sure my answer was right. That's something I have to do for myself to see that I can kind of store numbers right, and all that jazz. Negative 111. Okay, so what I'm going to do is take the inverse cosine of this thing here to solve for angle C. Now, personally, I think well, actually, now that I see the number, it's negative. I'm expecting an obtuse angle here, right? If I have if I have a negative ratio, that means I'm not in the first quadrant. Okay, I think you guys can agree with that. If I'm getting a negative ratio for cosine, that means I'm not in the first quadrant. So that means, when I do this, I'm going to be getting a, obtuse angle answer. And that's exactly what not what I was aiming for, but that's exactly why I chose to do this number first, just in case it was obtuse. Because only law of cosines will give me obtuse values such as that one. So 98.9, almost 99 now. It's about 98.9 degrees, and that is obtuse. So this is 98.9 up here. Okay, now I'm going to leave this thing as angle C. I'm going to go and store it as angle C, or C right here, as angle C, or variable C right there. Now I got to find angles A and B. And look, law of cosines to me is the longest thing you have to do here. A lot more calculations, a lot more mess ups can happen. And because I haven't done this yet, I'm going to go ahead and use law of sines to find one of my other two angle measures here. Now, the other thing I want to mention about obtuse angles really quickly, and I said I wouldn't be teaching, but I really have to for these again, is there can only be as many as one obtuse angles, there can only be up to one obtuse angle in a triangle. Even only one right angle in a triangle, right? You can have 3 acute angles, but once one angle is obtuse, the others are definitely acute. So I'm fine with using law of sines now to find out these other ones. Like if I find angle measure A here using C, I'll write these all straight up right here first. You can find them. Okay. Now, considering I'm finding an angle measure right here, it is also true you can multiply all sides by sine of A, B, and C and divide all sides by A, B, and C, and you can write this proportionally the other way as well. This might make you feel more comfortable when solving for an angle because your variable here is already in its own numerator. So this can be written as well, and I'm going to use it in such a fashion. Okay, let's say I wanted to find angle B first. Sure. Angle B. I'm going to be using these two together because I know side length C and I know angle C. And I know side length B This is the only variable, the only thing I do not know. So let's go ahead and do that. Sine of b, that's sine of b over side length b, which is 17, equals sine of, now this is about 98.9. I have an exact number in my calculator that I'm going to continue using, divided by side length c, which is 29. So sine of b is 17 times this mess. So b is going to be the inverse sine of this stuff here. And it's kind of crazy when you get a sine inside here. Really follow your parentheses when you end up doing your work for a problem like this. I just said law of cosines was hardest. Now I'm not so sure. No, but law of cosines probably least memorable, as far not least memorable, easiest to forget, you know, when it comes to getting the formula stuff out there. So, you know, I understand if you want to use it less and less, but with an obtuse angle to begin with and all that, it's really good to use it the first time. Okay, inverse sine, we're going to do 17 times sine of 98.9, oh, excuse me, of c, let me use c right here, about 98.9, divided by, close that parenthesis there, we're going to divide this by 29 here, and I'm still in degrees with all this, keep in mind. This answer is 35.385, so about 35.4 degrees. B is about 35.4 degrees. There we go. 35.4. Okay, so we got two of our answers there. Now, A can be found using law of sines, law of cosines, but also the third angle sum theorem for triangles, triangle third angle theorem. If I add these two together and then I add this with it, I should be getting 180. So if I add these together and subtract them from 180, I should be getting this angle right here. Now look, in this case, it's actually okay for me to use the rounded numbers because if I truly want these three things to, you know, add up to become 180, I think that's what I would do. But because I already have this angle inside here, remember this was B, if I add C with it, whoops, I put a plus sign right here. I wanted to put it right here. If I add C with it right here, then that's going to equal these two right here. 180 minus that number will give me angle A. All right, so A is 45.7 degrees about right there. So that's, whoopsie, hit the wrong button. So A, let's see, let's use green. A is, what, 180 minus the sum of 98.9 and 35.4, which is about 45.7 degrees right there. So I have all three right there. I solved all parts in that triangle. And all those do add up to 180, by the way, as well. So we're good. We're good. We got them. Number 46, I can't see it. There it is. Okay, number 46. Same thing. Solve the triangle, round answers to the nearest tenth. Okay, this time we have an angle measure. We need to find these other side lengths right here. Excuse me, this side length right here and these other angle measures right here. Now this side length is A. It's the little a right there. This is angle B, angle C. Now this is two sides and the angle in between. If you wanted to use law of sines, you wouldn't be able to because as we know, A over sine A, B over sine B, C over sine C, I'll keep it written because I'm sure I'm going to have to use it later, equals B over sine B equals C over sine C. If I choose two of these three sets of variables here, I will still have two of these three, like B and C, right? I would still have at least two variables still left to solve for, okay? I can use law of cosines, though. And law of cosines can be written in a different format to find the side length of something, such as A here. A squared will equal B squared plus C squared minus 2 times B times, not B again, minus 2 times B times C times cosine of angle A. So finding the side length that is opposite the angle that I know, I can now solve for that A there. A squared is, B is this guy here, C is this guy here. So 15 squared plus 11 squared minus 2 times 15 times 11 times cosine of 106. And keep in mind here, I'm just going to mention it again. This is an obtuse angle, and in the second quadrant, cosine of this should give me a negative number, which is just something to think about. I'll tell you why in just a moment to think about that. This is going to be 225 plus 121 minus 30 times 11 is negative minus 330 times this number right here. I'm going to leave it like that. I won't round it just yet. In fact, I'm actually not going to round it. It's actually better that I leave my answer, kind of, like this. You know what I mean? A squared is 225 plus 121 is 346. 346 minus 330 times the cosine of 106. And if I take the square root of both sides, then I'll be getting A here, this length. And not plus or minus, we're referring to a positive distance here. Square root of this honker here. Whoa, 106. Now, I want you to keep in mind again, 106 is an obtuse angle. When I take the cosine of it, it'll be a negative number. And negative times a negative is a positive. So in the end, this will be 346 plus a number, which means the number gets bigger than it does smaller. And that makes sense here because A is the largest side here. And if you don't want A to be confused with this guy's supplement, which is opposite 74 degrees, instead of subtracting some number, I'll be adding the same version of that number. That's what makes it so big. So, nothing that you have to know because the calculator is going to work for you here. But that's just a re-explanation one more time about the fact that, look, we use law of cosines in that first scenario for a big reason regarding obtusity. How about that? So A is about 20.9 units. What is it? Are there units here? Feet. It's about 20.9 feet. Now, as far as making sense of an answer, because I didn't do it in the last problem, and actually I think I do want to go back. As far as making sense of an answer here, if this is correct, this should be the longest side length of all three of them. 20.9 is longer than these two. Right now I'm trusting the answer a little bit to say that, yeah, that makes sense. And it's kind of within range as well. It couldn't be 26 or more, I'll tell you that much. Going back to the previous problem, just for a moment here, let's see if these numbers make sense again. 35.4 apparently was the smallest angle of the bunch, so its side opposite is also the smallest side length. 17 is less than 21. Here's the middle, here's the longest, and that's an obtuse angle. So that one did make sense there. What I have so far in this one looks to be making enough sense. This was about 20.9 feet here. Now I can use this value here to solve for angles B and C. I'm going to store this thing into A here because I'm going to be using it later. Again, whenever you get rounded answers, try your best, very much try your best to not use the rounded answer for future calculations. For example, let's say we find side length or angle C next here. If I want to find angle C, I'm going to be using law of sines, or I prefer to. Law of sines where sine of C over C, and C meaning 11, side length C, equals sine of A, 106, over side length A, 20.9, or thereabouts. So sine of C equals 11 times sine of 106 degrees, divided by 20.9. So C equals the inverse sine of 11 times sine of 106 degrees divided by 20.9. Okay, so I'm going to take the inverse sine here, and let's see what we get. And I will see if the answer makes enough sense when I get B on top of that one as well. 11 times sine of 106. And I've been in degrees this whole time. I've had no reason to use radians in this entire thing. Not to say that we will or won't have to, but just been no reason. So no changes there. C is about, looks like 30.4 degrees here. It's acute enough for me to trust it for now. That's the measure of angle C right up here, 30.4. Okay. I'll try and do this one without the calculator this time and see if I can get the measure of angle B or thereabouts. As we know, 106 degrees here, 30.4 degrees here. Measure of angle B will be found by taking 180 minus the addition of these two, or the sum of these two here. And that's going to be measure of angle B. So we're going to get about let's see, 180 minus 136.4. Okay, so that's going to be approximately 43.6 degrees. There's measure of angle B. Okay, largest, yes. Second largest, and third largest, yes. And again, I don't have the answer key in front of me here. I probably should, but trusting him. Number 47, find measure of angle B. Okay, so same scenario as we had before, only this time I don't have to use a law of cosines because what I see is here's side length B, here's side length C. I know angle and side length C. I know side length B, need to know angle B. Now I just got to know my ABCs. All right. Sine of B over side length B equals sine of C, 88, over side length C. Boom. By the way, I've been using units as answers every single time. Keep in mind of that kind of stuff as well. If this is for review for a final, it might not matter as much because, multiple choice. But if it's something else, just trusting your work, I think it's important. So multiply both sides by 10, we get this. Take the inverse sine of both sides, we will be getting a new value there. 10 times sine of 88, all divided by 11. All right, so it's going to be about the inverse sine here. Well, I think they said nearest tenth. So 10 times sine of 88, all divided by 11. Looks like 65.3 degrees. And I think that's all they asked for, measure of angle B and to the nearest tenth. Okay, yeah, that's it. So mission accomplished. Number 48, find the measure of angle A. Looks like, law of sines can be used here again. And when I say law of sines can be used, I'm actually also saying law of cosines can't be used up until we don't have the setup for law of cosines. There's certain scenarios, the side angle sides and what have you. But this one we can find measure of angle A here. Okay, so what do we have? Side length A is here, side length B is here. So sine of A over 13 equals sine of B, 108, over B. Let's see if we can do two steps at once here. I will multiply both sides by 13 and take inverse sine. I feel like almost when I write those two steps, like my hand starts to cramp because I'm like writing the same thing over and over. But you know what? People need both steps at times. I've never skipped out on the step really when writing it for y'all. So doing it now kind of feels a little uncomfortable, like I might have done something wrong. Getting away with murder. All right, here we go. Inverse sine of 13 times the sine of 108. This is divided by, close parentheses first. This is divided by 40, and we are getting 18. Okay, 18 degrees, 18.0. It's around 18.0 degrees. That's it. Look, they're not asking for anything else from that. Just practicing your law of sines and law of cosines and such. And yeah, we're set with those ones. Number 49, graph the function using degrees. Okay, I'm going to get rid of the calculator now, actually. Just hide it. Graph the function using degrees here. And they're saying using degrees, so look, I'm going to use degrees. It's okay. I'm not used to using them here, but when I do use radians, normally I go in terms of, pi over 2, pi, 3 pi over 2, 2 pi. So, what, 45, see, I got it wrong already. 90, 180, 270, 360, stuff like that. So, all we're doing is changing these variables here. Maybe I could erase them and just write them afterward, and then negative 90, etc. this way. And I'll add some more if I need to, but but that's the scaling. I think it's good right there. I could keep adding on later if needed. This is going to be 1, 2, and 3. And negative 1, negative 2, negative 3. Okay, as far as 3 sine of theta goes. Now a basic sine graph. If I paste, nope, pasting doesn't give me that old set of axes before. Using a regular sine graph here, we would start at the origin and we'd go up and down, etc. Where its amplitude would be 1, its period would be 2 pi, or 360, and this doesn't seem to have any shifts, doesn't seem to have any period changes. The only change seems to be from the amplitude. This is a y equals a times b times x minus, a times sine of b times x minus h inside this quantity plus k, where your period would be 2 pi over b, or vice versa. 2 pi over p is your b and stuff like that. Your b value is 1, so that's unchanged. Theta's right here, blah, blah, blah. So no shifts, no changes there. I'm going to start right here. I'm going to be rising and a fallen, and I'm going to have a period of 2 pi, or 360. So that means halfway through, it's going to go up to 3 with an amplitude. Halfway through, it's going to get back down to 180. I'm going to use a different color. And it's going to bottom out at -3, and it's going to come back up to 360. So the graph, which won't be a pretty looking one on my end here, go up to here, so fly up there, up. Now I'm coming back down, plummeting. Not pretty at all, sorry about that. Down to here. It's really hard because I'm not touching the part of the screen that I'm looking at or anything like that. Doesn't quite get it much easier. 360, and on the other side, sine is an odd function, if you remember what that is. Symmetry across the origin. So it has rotational symmetry, up and down to 360, and I could do it over and over, but I'm kind of embarrassed by the look of my drawing. I look like I'm a toddler. But there's your graph that's using degrees, getting that one out there. There's 49, again, no shifts. Number 50, using radians. We get to use radians. And this time here, it looks like there's going to be a period change, but there's no shift in the graph itself. Okay, a default cosine graph, which I've drawn twice so far in this video, starts off at 0, 1, and then it goes down and comes back up and such. And when it reaches a full period by default, that would be at 2 pi, going all the way down, all the way back up to 1. Now this amplitude is 1, so when it comes to this stuff, maybe I'll call this 1. I'll keep that as 1. And as I said, I do pi over 2 and such, pi, 3 pi over 2, and 2 pi. What's going to change? Well, actually, I'm not going to do this, because what's going to change here for me actually is the period. Okay, if the general graph here is a times cosine of b times x minus h plus k, and what I'm looking at here is 1 times cosine of 4 times x minus 0, x minus 0, or theta minus 0, plus 0. 4 is my b value, and my b value can determine my period here. 2 pi over 4 basically says I'm going to be cycling through this 4 times faster than I normally would. I'm going to be covering 4 different periods of this over the course of 2 pi. So the entire period itself is pi over 2. So what I want to do here instead is make sure that I can hit 4 intervals here before getting to pi over 2, at just pi over 2. Right? I'm changing the scaling of this. Another 4 would be pi. This would be going out for quite a while here. Now what's in between is a quarter of pi over 2. A quarter of pi over 2 is pi over 8. That's this guy. Half of pi over 2 is pi over 4. 3/4 of it is 6 pi, this should be an 8, is 6 pi over 8. That doesn't sound right. 3 pi over 8. And there's pi over 2, etc. So you can get those by taking, you can add pi over 8 each time, stuff like that. But those are those increments there. I'm going to leave it like that for now. I think that's enough to cover the spread, if you will. There's no shift here, so for a cosine graph, I'm going to start at 0, 1. No amplitude change. Now I'm going to be going down here, down through. So this will look like any other cosine graph you had. The difference is the period here. And I changed that through the scaling of my increments. Otherwise, this would appear a lot skinnier. You go to Desmos, use your graphing calculator. This would be a lot skinnier than this. And whoops, that was going so well too. And it'd be going up and down like that again. And cosine is an even function in that in its basic form, it is symmetrical across the y-axis. So you can reflect across there and up and down. And That's the look of the graph there. Like I said, it should be skinnier. Note, we haven't gotten to 2 pi yet. This is just pi. So compared to this, it would be a lot skinnier. There's number 50. Okay, and so that closes out the previous, I don't know if it's the previous chapters, but that closes out that first section there. We have a 1 through 50 and then an answer key. Now you have this other stuff, and it's going into a chapter 6, I think, they say, even though we've been doing probably a little bit of chapter 6 here with the law of sine stuff. Anyway, what we're going into here has some multiple choice, which is awesome. For some reason, it starts at number 4. For whatever reason, then it skips 1, 2, and 3, and then it ends at number 9. So I only have 6 more problems to go. I think they're only 1 part each. They may be longer problems, but you know we're still actually in decent time, all told, for all these problems here. Number 4, determine the number of acres in a triangular parcel of land if the lengths of the sides measure 1507, 1750, and 970 feet. There are 43,560 square feet in 1 acre. So there are a couple things that are involved here. Number 1, determining area. And I'm going to be using law of cosines like I did last time to determine that. I don't know if this is anywhere drawn to scale. I'm just drawing a triangle with lengths because of the triangular parcel. Number 2, converting to acres from square feet. Sorry, my other computer was acting up. Converting from square feet to acres. So we're going to find area first. 1507, 1750, and 970. Just to be accurate enough, I'm going to do these in, this is the smallest one, this is the next smallest one, and then here's the largest one. Okay, so what I have to do here is I have to find this area. And again, not Homer's law, what's his name? Heron's formula would be one way of going about it. Again, I'm going to do what I did last time. I'm going to call this angle measure x, this unknown right here. And I'm going to declare this as my base early on. My base is going to be 1,750 feet here. 1750 is B. And my h value I'm going to determine here after I find the angle measure x. So I can use what I did last time. This time I'll try and speed it up a little bit more now that you've seen it once from a previous problem here. Let's find out x here using law of cosines. Cosine of angle x will be taking the square of these two and adding them. So 1750 squared plus 1507 squared. Don't expect me to not use a calculator here. I definitely will. Minus 970 squared. It's the one opposite, minus the side opposite the angle that I'm looking for. Divided by 2 times 1750 times 1507. I'm almost compelled for right now to just compute what this number is now. And I wouldn't mind if you did either. Look, there's nothing wrong with that. The problem is making sure you get your order of operations in. For example, I have to open this with parentheses if I want to do this right. 1750 squared plus 1507 squared plus, or excuse me, minus 970 squared. That is in the numerator. In the denominator, close, divide. In the denominator, open 2 times 1750 times 1507. Now again, I'm going in blind, meaning I'm going in without the answer key, so I do trust that everything I do here is going to be accurate to what it needs to be. You know what? This number's not bad. It had to be between -1 and +1 to take the inverse cosine of it, which is the next step to find the angle measure for x. So inverse cosine of that previous value that I got will be my angle measure x, 33.61 degrees, whatever it is. I'm just going to put about 34 degrees. X is about 34 degrees. Because remember, what I'm going to do is use my calculator and keep this value stored anyway. So I'm going to store this into x. Okay. And I'm going to leave that there. It's probably just going to be the next answer I use anyway, but just in case it's not. Let's find out what h is now in terms of that x value that we have. The sine of x, sine of 34, is opposite, which is height, h, divided by hypotenuse, which is 1507. So x, or excuse me, h is 1507 times sine of 34. Remember, it's not really 34. So My area for this entire thing in square feet, the area of this thing will be 1/2 base times height. Okay. Again, just don't lose yourself in your work and everything will be just fine. So 1/2, and make sure you do order of operations correctly, otherwise everything goes kaput. Times base times height. And look, if I type something wrong, it's always my apologies. I normally catch myself before I do it here. That's a lot of numbers there, but I'm going to keep, oh shoot, I used 34. See, I shouldn't have done that. Let me use the previous times height. This is X right here, not 34. See, I almost lost myself there. Should be that number. Look how different these two things were right here. One I used 30, I guess this is a good example of it. One I used 34. The other I used X, which is 33.6. Look, those are different answers. That's 8,000 different. So, about doesn't cut it here, right? Understand when I say that you can't just use rounded answers. But this area here still is about 939. Let me try that again. 729,939.4244 square feet. What we have to do from here is convert this into, I can't write anymore. I've run out of steam. What we have to do is convert this to acres. Now they give us the unit of measurement there. They tell us there are 43,560 square feet in 1 acre. So what I'm going to do here, it's more of something you might have done in physics or chemistry. It's called unit conversions. So what I'm going to do is I'm going to take my 729,939.4244 square feet. And I'm going to multiply that by, for every 1 acre, there are, 43,560 square feet. What happens here with these units is I've actually canceled out square feet with square feet. Now I'm left with taking this number and dividing it by this one here. That gives me how many acres there are going to be about in this thing here. And you know what's the good thing about this problem, assuming there's no other issues here, is it's multiple choice. So I get to see that we landed on one of the right answers if all went to plan. So it's about 16.757 acres. I'm going to write all of those because I don't know what the answers look like. 16.757 acres. It might say about 17 acres or 16. In that case, I'd probably say 17 before 16. So let's see what we got. 16.757, moving up. 16.8, right? What did we say? About 16.8 acres, I guess, would then work here. What's really scary is the none of these. I looked at this and said, uh-oh, we're not sure. It looks like it's going to be this one rounded to the nearest tenth there. And look, these numbers aren't far off from each other. So you could have gotten something different with this number here. Okay, it could have changed your answer. So make sure you don't use any rounded numbers prior to. Whoops, just dropped my pen. All right, number 5. Ooh, there are a few. Find the component of the vector. Oh, that's multiple choice. Find the component form of the vector at the right. Okay, let me shut this off for a while. I don't need it. Here we go. So vectors. Vectors have two things, magnitude and direction. Component form is a way of stating how far over it goes from one point to another and how far up and down it goes from one point to another in terms of x and y. From -4 to -2, it has traveled 2 units. From -1 to -5, it has traveled 4 units downward. I'm looking for the component form of 2, -4. And that's going to be this one right here, B. Now, just so you know, magnitude and direction are the only properties of vectors. Its position in a coordinate plane has nothing to do with it. So 2, -4 could have existed over here if this went 2 over and 4 down. Doesn't matter where. So this still applies as long as we use the diagonal brackets, the angle brackets, like these ones right here for the answer. Number 6, find a unit vector in the direction of V. Here's V, 3 vector I minus 3 vector J. Okay, what I'm going to do is start this vector at the origin because, you know, we can put it anywhere we'd like to. 3i minus 3j, that's a linear combination that can also represent this thing in component form of 3, negative 3. Meaning from head to tail, we start here. We will run 3. We will fall 3. That's 3, negative 3 right there. This is your vector v. Okay? Vector v looks like this. Vector u is a unit vector in the same direction as this one. Now, you might already know what to do in order to figure out this answer stuff for here, but let's break it down a little bit more than that. Vector v here, I could find the magnitude of vector v right here. Look, you can get the answer u by lucking out is what I meant to say, because this problem has lower task difficulty. However, it could be harder. What I might do is find the magnitude of vector v right here, which would be the square root of 3 squared plus negative 3 quantities squared right there. The I and j, the x and y components of the vector there. Square root of 9 plus 9 is square root of 18, which is 3 root 2. Now, you might know that, 3 to 3 to 3 root 2, like a 45, 45, 90, which is exactly what it is. So vector v is 3 root 2. Vector u is 1. The magnitude of vector u is 1. So what we're trying to do here is say, using this component form here, this 3 and negative 3, vector u is similarly the same number of times smaller in every direction, just as it is in the actual vector itself. So if vector u is 3 root 2 times smaller than vector v, then vector u's components are 3 root 2 times smaller than 3 and negative 3. So vector u is 3 divided by 3 root 2, because it's 3 root 2 times smaller, and negative 3 divided by 3 root 2. Okay. Now this here reduces to 1 over root 2, which is root 2 over 2, comma, negative root 2 over 2. Now this is component form. If you can see all your answers here, they're in terms of linear combinations I and j. So I is with the horizontal unit vector here. So this is I root 2 over 2, or it looks like here, I'm looking at this answer, root 2 over 2i, vector I, plus negative root 2 over 2, so minus root 2 over 2 times vector j right there. I know this problem went a little bit all over the place here. Let me recap it and then state that there are some other review videos you can check out. I might link you to something here. But vector u is a vector of is a vector of length 1, of magnitude 1. Vector v apparently has a magnitude of 3 root 2. So vector u is exactly 3 root times smaller than vector v, not just right here, but also here and here. In other words, vector u's components here are root 2 over 2 and negative root 2 over 2. Those are 3 root 2 times smaller than 3 and negative 3. We needed those to find out the linear combination of vector u. It looks like the answer here is C. But we did the stuff in Chapter 6, so Chapter 6 review video is in order there. You can find other ones with unit vectors and such there. Number 7, given vector v is I, which means 1i, which means 1i plus 0j, which also means linear combination of 1, 0, right? Vector I is the unit vector in the horizontal direction. And vector w is 2i minus 3j, which would be 2, negative 3. Let's find v dot w, vector v dot vector w. Now the result of v dot w, when you multiply two vectors here as a dot product, your result is a scalar value. What we're going to do is take the x components and multiply them together, 1 times 2. Then we're going to add this with the components of vector, the y components of both vectors together, 0 times negative 3. Again, long day. I'm lost in my words. My apologies. So v dot w is 3 plus 0, which is 3. The answer there is a scalar value, which is 3. None of these. Wait a second. 1 times 2 is 2. See, it's been a long day, man. 1 times 2 is 2. There we go. It's 2. Good thing 3 wasn't an answer. I would have circled it and moved on. But anyway, it can't be this. It can't be this. It's not, your answer is not a component form of anything there. Your answer is a scalar value. So there you go. Which of the following pairs of vectors are orthogonal? Now, orthogonality is referring to perpendicularity of vectors. So which of the following are perpendicular to each other? Now, in order for vectors to be perpendicular, you have a lot of ways of going about them. You can think of these things in a way as a way of finding slope, and in which case you actually might be able to find the answer just by looking at them. I'm sure if I looked hard enough, I could actually find out. And the answer could be none of these. What I could also do is look back at dot product. Dot product gives you a scalar value. What the scalar value here gives you is how much work one vector is doing on another in its particular direction. We used a plane example before. If I have an airplane, right here, and it's flying this way, and let's say a crosswind is blowing in at it, and I'm doing this kind of in 3D, so it's going right at it, like perpendicularly. If there's a crosswind going at it right here in a plane that's going this way, yeah, it might push the plane this way a little bit like that. However, it is not affecting its speed in this direction at all in a fundamental sense there. The work done on it is not affecting the speed in the direction that it's going. So what I'm looking for perpendicularity is that if you take the dot product of two numbers and the result is 0, I'm going to look at part A. If you look at the dot product of two numbers and the result is 0, that means your vectors are orthogonal. I will then show that afterward by drawing them both and saying, yeah, that makes sense. So V dot W for part A here would be 4 times 2. Excuse me, 4 times, sorry. 4 times 2. That's this times this plus -2 times -4. Okay, so that looks like 8 plus 8, which is 16. So A is out. B, my vector V dot vector W. Please don't make it be none of these. I don't want to do all of them first. Or please don't make it be D as well. 3 times 9 plus 1 times 3, which obviously is not 0. That's 30. That's 30. So it's not B. C, doesn't look like C is going to be possible here as well, because we're going to be multiplying one of them by 0. This is 1, -1, and 1 and 0. So this will be 1 times 1 plus -1 times 0, which is 1. So the answer is either D or E. So it does go down to the wire here. D, vector V dot vector W. We're going to get -2 times 1, that's the I in W, -2 times 1, plus 1 times 2. Okay, so it looks like -2 plus 2 is 0. So it looks like the answer here is D. Now, if I want to look at this in a more visual sense here, looking at these two vectors in part D and claiming its orthogonality, again, you can think of it in terms of slopes here. It's all about opposite reciprocal. You might not see it right off the bat, though, because maybe you didn't reduce the fractions of the slopes and what have you. But over here, if I start them both at the origin, if I start both the heads at 0, 0 here, for vector V, I can run 2 to the left and rise 1 up. So that's over 2 up 1. That's a slope of -1/2. Okay, so here's vector V. Vector W runs 1 and rises 2. So run once to the right and rises 2. Whoops, right here. So here's vector W. So there's the orthogonality there. Those two are perpendicular to each other. There's 90 degrees. Again, slope of 1/2. The slope of W technically is 2 over 1. And the slope of vector V technically is -1/2. So there's orthogonality again in a nutshell. But the dot product is 0. That's the check. Okay, this is the last problem of all of them. Final. Rewrite in trigonometric form -2 plus 3i. Okay, trig form. Whoa. Okay, trig form has this crazy thing going here. In trig form, we're going to be getting, first of all, this is a complex number. They can denote that as z. So if I write z equals, just forgive me there. Z equals r. R is going to represent the absolute, the distance, the absolute value of this number here. This will be times the cosine of our theta value that we're going to find, plus I times the sine of the theta value we're going to find here. Okay. Now, I is representing the imaginary component as it's going up and down on the imaginary axis. Cosine goes left and right. These we're going to be representing kind of as the unit components, if you will, because they're going to multiply by the magnitude outside here. And when I say all that stuff, unit, blah, 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 these aren't vectors, but they're in the same chapter as vectors because they do kind of work together. You know, we can write this stuff in forms for vectors as well. And so, we can do it here. But this is not a vector I. This is the imaginary component I here. So negative 2 plus 3i, that is 2 over on the real axis. Remember, this is not x and y. This is real and imaginary. 2 over on the real axis, 3 up on the imaginary axis right here. Here is the point, negative 2 plus 3i in blue. Here's what we have. We have a little distance right here. I'm going to call that r. Okay. There is a theta value that's actually right here that we're also going to be finding. Now, in doing so, it might help us to find theta prime, the reference angle inside right here, to find what it is we're exactly looking for. Okay, by knowing that this is a negative 2 and this is a positive 3. Doesn't matter that the I is there, I just want to call it a 3. So negative 2 and 3, we can find this theta prime to find this theta. We can also use it to find the magnitude. Okay, how do you find that magnitude r? Well, r squared equals negative 2 squared plus 3 squared. Pythagorean theorem. So r is going to be the square root of 4 plus 9, which is the square root of 13. And as you can tell, all these answers are root 13 here, so there's no surprise there. If you don't get root 13, either your answer is none of these, or you might want to retrace your steps and see if there's anything else you got to do. Okay, so r is square root of 13 there. Now, next thing I'm going to find here is theta prime. Theta prime is the reference angle inside this particular triangle, where I would be taking the tangent of this thing here in order to get the ratio of 3 over negative 2, or negative 3 halves. So the inverse tangent, theta prime is the inverse tangent of negative 3 halves. That's negative 1.5 also. Okay, this looks like a good time for me to go back to the calculator here. So let's bring that back up. We'll take the inverse tangent of negative 1.5. Oh, that's a minus symbol. Negative 1.5. And I'm going to get negative 56 degrees. Now, you have to know what this number kind of is in reference to, right? What we're really dealing with here, we want to deal with a positive number in the end. So that's why drawing the picture is very, very helpful here. So it's about 56.3 degrees there, right? Negative, positive, what have you. Question really is, what is this theta value? This is what we need to find out. You can see that this is going to be 56.3 degrees less than 180. We got to take 180 and, whoops, not right there in our calculator. We got to take 180 here and subtract that number because the number is already negative. I'm going to add it. Okay, so part of it is just knowing where you are in your drawing. That's going to be most important. So this number 123.69, and I don't know what they round to here. You can probably already figure out your answer here, 123.7. I'm guessing the answer is going to be B. 123.7 is what I'm going to round to for theta. Okay, so we got theta, not theta prime. The actual angle is 123.7 degrees rounded here, and I'm going to keep that one because that's what they use. And we just got to write this in trig form. Okay, the whole point of trig form is leaving things in terms of trig only, not relying on the actual numbers here, but things that involve trig, the magnitude and direction. So if theta is 123.7, if r is square root of 13, and if z equals r times the cosine of 123.7, which, by the way, is just about negative 2, cosine of 123.7, plus I times sine of 123.7, which, by the way, is just about 3, then we have our answer there. That would be it. Boom. And that would be the answer to part B, B right here. My guess is all of these other answers, and I can really see it from part A right here, all the other answers are this same reference angle built in different quadrants. For example, 56.3 could be built in the first quadrant. 236.3 is 56 under or more than 180, and this is probably 56 less than 360 right there. So they kind of all have the same answer there, and they're, this is one of those, they can trick you with multiple choice kinds of things, right? This is the one answer that works here, that when you take the cosine of it, so check this out. Cosine of this previous answer, we're supposed to get -2. Oh, excuse me, times root 13. I was scratching my head there for a second. I said, what? Am I in radians? Times root 13, I should be getting -2. God, no wonder why what I was saying was kind of strange. But anyway, times root 13, we get that answer there. And so that cleans up. It should be negative though, right? That's the whole point. The other ones would be the same numbers, but they would have different signs, a +2 and a -3 and what have you. So there's the final answer. There's the final work. That's the final problem of this final review. I am out of here. Fiend.